Hi there, my name is Alex, and in this episode, we will continue our Sim to Real pipeline series, and we'll focus on how to control our PX100 PincherX100 robot from Sim using IsaacSim from Nvidia. So first of all, we're looking at the Sim host right now, and we have Ubuntu 22 LTS installed there, and we'll install ROS2 Humble. And this is the installation procedure, which is a vanilla installation procedure available on the website. And then, yeah, as we start using terminal, we don't want to forget sourcing the ROS2 environment. We have this Robotics ROS manipulators GitHub that we could use with this ARM PX100. And there's a ROS control, there's a control examples as well as Python examples. But the thing is that this is built for ROS1, and we'll be using Dynamixel SDK directly for relaying messages and joint state messages to our robot. But this is just a quick illustration of what's available from Trossen AI on Robotics ROS manipulators GitHub. Actually, I had another environment with the ROS1 installed with Jetson Orin where I actually use those examples and they work fine. But again, ROS1. Then in this episode, we'll also be using Action Graph inside of IsaacSim. And this will help us to publish joint states onto ROS topics. And this is just an example of how such graph may look like. On SimHost, which is, again, this is the laptop. It's essentially Microsoft Surface Studio 2 laptop with the GPU, RTX 4060 laptop GPU. We have IsaacSim running. And we build a graph, action graph. And as you can see that as the simulation is running, we're capable of moving different types of joints here. And this is what will generate the messages. The URDF import did not work completely, but this will be a subject for a whole new separate episode. When we will describe all the issues and all the solutions for URDF import, comparing to what we saw earlier with RVS. Then we have two terminals. In one terminal, we see the ROS2 topic list. That means that we launched IsaacSim with the ROS bridge. So we have parameter events, we have ROS out. We'll come back to this caveat of how to properly launch IsaacSim with the ROS2 bridge later in this video. But for the moment, we have joint states topic published and advertised. And onto this topic, we publish in essentially right now with the graph running and simulation running. We publish in joint states for all of the joints available for PX100. So in the second terminal, we also source the ROS2 environment, and then we inspect joint states messages on the topic, joint states topic. And as you will see, at this point, again, we launch the echo command. Yeah, and now we'll just, in simulation, we will be moving the joints, and then you will see that the appropriate changes will be reflected in the terminal as we're listening to those joint states changes. So this is because we have the action graph, we have the simulation running, and we publish in by means of the action graph, we publish in messages onto joint states topic, ROS2, and the terminal is listening to that. All right, so this all worked. Now we can move on to the caveat relative to how you actually launch IsaacSim with the ROS2 bridge. So we're still looking at the sim host, and we have the IsaacSim selector starter script. And if we start that, we have several options for the RCLPy library, which is the ROS2 Python library for writing ROS2 nodes. So with this client library, so first of all, we have the ROS bridge extension that we have to enable as on the screen. And then we have this use internal ROS2 libraries options. So if we select Humble as an internal ROS2 library, this is not what we want. So we'll inspect the effect of this, and when the IsaacSim launches in the second terminal window, where we see the results or the process of launching IsaacSim, we'll have all of the different extensions, all of the different libraries loaded, and we'll be looking for the RCLPy library. As you can see, it says attempting to load internal, and initially attempting to load system RCLPy, could not import system RCLPy, and attempting to load internal, and then ultimately it loads the internal RCLPy. But this is not what we want, because in fact we want RCLPy from the ROS2 installation, from the ROS2 environment. So if we just do it again and launch the, I'll just clear the terminal very quickly and launch the launcher script. And this time we'll take out the use internal ROS2 libraries while still enabling the ROS2 bridge extension for IsaacSim. When we launch this, supposedly we should load the right RCLPy library. But as the output will show, there's one more step required for you to launch this properly, because in the output, it's still showing that we're using internal RCLPy library, which is good for like quick demos, but definitely for our purposes, we want the system ROS2 environment RCLPy. To properly launch it the way we want, for all of the communication will take place, we have to source the environment, ROS2 environment, in the terminal first, and then launch the script. And then as everything works, you will see in the demo at the end of this video that the ROS2 communication and messages will be visible as a part of a ROS domain ID, which is the default 0, and both of the SIM host as well as my Jetson that controls and is connected physically to the robot through U2D, which is the USB to Dynamics L2 connection, because both of the machines are on the same network and belong to the same ROS domain ID 0. We will be able to publish from onto topic messages, onto topic joint states from SIM host, and we'll be able to receive it on the Jetson and then relay it to and kind of command our robot appropriately on Jetson. So at this point, we're just showing that we launched everything properly on the SIM host, and we're capable of getting to the same state where we were with our model with our physics inspector, with all of the joints necessary. And then also, like, as we loaded the scene, you can also see that we can control all of the joints. Again, the URDF import challenges will be explained in a separate video, because at this point you see that the gripper fingers are not properly aligned and there's no collisions properly enabled, and the whole story about different types of joints will be, from revolute joints to fixed joints to mimic joints, will be explained there. So now let's switch gears to Jetson. This is the machine and computer that is connected to the physical PX100 robot. And in this case, we have also installed ROS2 Humble onto Jetson with Jetpack 6.2. And we will look into, again, how we will be able to catch the messages on joint states ROS2 topic, as it was explained before. And as you can see, that what we publishing from SimHost, we're capable of catching on the Jetson connected to the physical robot. Then in terms of what else needs to be there, we mentioned there's a Interbotics GitHub, which allows you to control the robot. And in this case, again, we're just kind of scrolling through the installation procedure of ROS2 Humble. And just again, same idea of also in terminal, we have to source the ROS2 environment. But the difference between, again, us using that Python SDK from Interbotics and using more direct Dynamixel SDK, which is one of the ROS2 packages, is that the Dynamixel way is ROS2 compatible. The Interbotics GitHub and those packages, they are for ROS1. That's why they work for me on ROS1 enabled Jetson Orin Nano, but my Jetson Orin AGX is ROS2 enabled. Now let's look at the servers, motors, and the supported Dynamixels. So we have this XL430 W250, which is exactly for the Dynamixel SDK, this is the exactly supported motor type, server type, comparing to like what we have physically on this PincherX 100. So we're looking at the Dynamixel workbench, which is one of the ROS2 packages, which describes exactly that aspect of supportability for the server type that we have. And then if you look at the ROS2 Dynamixel SDK package, you will see this is for Robotics Dynamixel SDK. We have, like you can see on the screen, the type of the server that we have on PincherX 100 for its joints, to control its joints. So that's why it's important to use this approach, which is compatible with the ROS2 installation. And then to control it subsequently, we have this GitHub gist published, which is taking advantage of RCLPy library, the ROS2 Python client library for writing ROS2 nodes. Then we're using joint states and the sensor message package. We map in different types of joints available on the physical robot, which is per the spec. And then after this, we have the commander, which is, again, it kind of like opens the connection through this U2D2 to PX100 link. And this is essentially an adapter interface controlling interactions with the PX100 through dynamic cell servo motors. Then after this, we have to enable the torque on all joints, and then also, like as you can see, that we can subscribe to joint states ROS2 topic. And for the simple demo, we can just publish onto a separate topic, which is called joint commands. And for fully synced with the same host demo, which is a little bit more sophisticated, you'll see we subscribe directly to joint states. And this will give us the state of all of the joints that will be reflected on the robot when this commander is running. And we're also going to launch this commander as a standalone Python script, because for simplicity, we're not building any ROS packages here, just again sourcing the ROS environment and launching that script in the terminal. Again, first demo, for starters, we just submit states of our joints and commands to our joints, representing states of those joints and angles of those joints in radians. And the second is we'll switch over to basically listening to what IsaacSim from SimHost is publishing onto joint states. So in order for this to work on Jetson, we have to install a couple of libraries. So one of them is the Python 3 serial library. And also, obviously, we have to install the ROS Humble Dynamic Cell SDK. And then once we install that, we can take a look what we installed in the environment. And we can see that the Dynamic Cell SDK is present, as well as a few more libraries, a few more packages for us to be able to use and relay messages. Then we have to source the environment in all of the terminals, as usually, not to forget that. And then after this, we can actually do sourcing the environment and launching the standalone commander script, which will enable the torque on all of the joints. So we'll be able to manipulate with them, and also get ready and subscribe to a topic which is called joint commands. And for the first quick demo that we will show at some point at the end of this video, we will be able to submit something directly to the joint commands in terms of angles for the joints, and then the robot will react to that right away. So this is an example of submitting a joint command in the format compatible with the message joint state. We specify all of the different names of different joints and supply a desired position. And as we do this, our robot connected to the Jetson AGX will move in this case, it's a wrist joint. Yeah, and then if we want the sim host to be in full control of what robot does, and when we move something in the sim host IsaacSim in terms of the joint positions in physics inspector, and this gets reflected on the physical PX100 robot, we just switch over to using joint states in the commander script that takes advantage of Dynamic Cell SDK and connects through U2D2 adapter. And This way messages make their way from the sim host IsaacSim when simulation is on to the robot. Now let's look in the real world. So the first demo is submitting command onto join command. And as you can see, the robot is moving its wrist. And then we'll just return it back to its home position. All right, so this worked, perfect. Yeah, obviously we have to enable the torque for all of the joints, so that's just a quick caveat. And the second demo is controlling a robot from the sim host. So the robot is connected to Jetson Orin AGX. And as you can see that on my laptop, I have IsaacSim running. And then the messages are flowing right now through joint states topic. So this worked perfectly as well.